So 10.3, periodicity of chemical properties. We need to look at the chemical properties. And the most important thing when it comes to chemical properties, as you might have also seen in IGCSE, are the formation of oxides or how those oxides behave, or the formation of chlorides or how those chlorides behave. Usually chlorides are something that we don't discuss at that point, but oxides is definitely something that we have discussed before. If you remember your IGCSE book, that was a part of acids and bases chapter. We discussed the oxides, how they form, or whether we are able to dissolve those oxides in water and test them with a litmus paper or not. There were four main bifurcations for oxides: acidic, basic, neutral, amphoteric. So this kind is the kind of things that we have discussed already over there. So we're going to pick up from the same pace over here. Let's start with a simple practical activity 10.1 in which period 3 elements react with oxygen. Now, when sodium reacts with oxygen, it reacts vigorously. Sodium is a very reactive metal, and when it comes to that, when heated and placed in a jar of oxygen, the sodium burns with a bright yellow flame. The flame color of sodium has been a part of IGCSE, so we're going to do the same over here. The main product when sodium burns in a limited amount of oxygen is white solid sodium oxide that we stick to because sodium can make different oxides. Sodium peroxide is also possible. But since we are not going to go with sodium peroxide, so we stick with this equation and this specific reaction. Now, moving on to magnesium, since we're talking about group period 3, so with sodium, magnesium, so on and so forth, boron, not boron, aluminum, silicon, and so on. So magnesium also reacts vigorously when heated in oxygen. It forms magnesium oxide. Aluminum metal protects itself by forming a layer of aluminum oxide, but powdered aluminum does react well with oxygen. Both metals burn with bright white flames. Remember, you need to be very specific with flame colors, and flame colors have been a part of past papers. You are also doing this specifically for paper 3 and 5. Okay, moving on. Silicon reacts with oxygen to form silicon 4 oxide. We don't usually go with any kind of adjectives or colors for that reaction, so let's stick to that way. Phosphorus next up is reacting vigorously with oxygen. A yellow or white flame is seen. Clouds of white phosphorus 5 oxide are produced. Phosphorus 5 oxide is given as P4O10 or P2O5. To be true, it can exist as a dimer, so P2O5 can really be written as a P4O10. Okay, so sulfur powder, once ignited, burns gently with a blue flame in a gas jar of oxygen gas. Now, this actually happens with a blue flame. That is something that we specifically explained back in IGCSE. So it's the same over here. Toxic fumes of sulfur dioxide gas are produced. Now, keep in mind that we are talking about not just the formation of oxide, but how the oxides may look like or how they may behave along with one or two of their physical properties. For example, this one is a white solid. For example, both of them are powdered white solids. Uh, we don't usually talk about this one, but when it comes to phosphorus, clouds, which means they're producing small particles of phosphorus 5 oxide solid, which act as a cloud. Now, toxic fumes, which means it's gaseous. Further oxidation of sulfur dioxide is possible. It does give you sulfur trioxide. Systemic names are sulfur 4 oxide and sulfur 6 oxide. This is also possible with the help of V2O2. I think it better be if you go with V2O5 catalyst. However, V2O2 is also possible. Vanadium oxides are good at converting sulfur dioxide into sulfur trioxide. And since vanadium can form different oxides, it's not just limited to +2, it can have +3, it can have +5 states. So yeah, that is possible. V2O2, V2O3, V2O5, there are different oxides are possible, and most of them act as a catalyst for this reaction. Well, keep moving on. Chlorine and argon do not react with oxygen. It does not that it's not that they do not form compounds at all, because you are going to see something like this in your past papers. So you might think that chlorine can form oxides. Yes, that is true. Chlorine can form oxides under very harsh conditions, But since we're not talking about any harsher conditions over here, we haven't increased the temperature to 300, 500, or 1000 degrees for any of these reactions. So that's why we have excluded any kind of oxides which are not made under easier conditions. So moving on, reactions of period 3 elements with chlorine. Now, before I move on, let me tell you, we haven't talked about the kind of oxides that are forming, whether the oxide is soluble in water or not, or the oxide can be tested with a litmus paper after forming a solution in water. It's going to be acidic or not, something like that. So all of this stuff have been done in IGCSE before. So that's why they consider it as a prerequisite, and they do understand you already know that stuff. So it does not mean that if it's not written over here, you're not going to do it. Make sure you understand for this kind of reaction to be carried on in this way, okay? Or that this can turn blue to red for litmus paper, or this may be concluded as an acidic oxide. And as soon as I consider it as an acidic oxide, I hope you understand that this would react as an acid for a neutralization reaction and is capable of forming a salt along with water in this kind of reaction. So I hope you understand that you can concur for all of these as a part of something that you have studied previously. Okay. So I've done it for just one oxide. Make sure you understand for it for all the oxides. And when it comes to silicon, this might be a little bit questionable. Now, I hope you understand all the metal oxides usually here are basic oxides. Aluminum oxide, however, is amphoteric. The silicon is acidic. And moving on, phosphorus, sulfur are all then acidic oxides. So I hope that clarifies it. Let's move on to reaction of period 3 elements with chlorine. Moving on with chlorine, we plunge into a gas jar of chlorine, the sodium metal. There is going to be a vigorous reaction. We're going to form the table salt we eat every day, sodium chloride. Magnesium and aluminum also react vigorously with chlorine, uh, so much so that we do not try to go with these reactions in school lab. If we do, we try to be very careful, and those are usually not student performed experiments. They are usually demonstrated by teacher only for all three of these metals. Silicon reacts slowly with chlorine as it does with oxygen, which produce silicon 4 oxide, silicon 4 chloride. Now, phosphorus is going to react slowly with excess of chlorine. To be a little more clear about this, phosphorus can react with chlorine in such a way that it can form PCl3, but PCl3 isn't a very stable chloride. So if there is excess, PCl3 can easily be converted into PCl5 automatically upon further chlorination. So this is what you get. So they try to stick to this one as a final equation. Okay, you might face questions here and there related to PCl3, not because of the formation, because of something else. Remember, A-level sticks to the course outline and give the questions in a very clever way. They might give you a scenario about a different thing, but I still ask you a question related to your book or what you have already done in the book. Sulfur does form chlorides, Cl2, F2Cl2, but you do not need to cover those for your syllabus or examination. It's so clearly they've drawn a boundary over here. Argon does not form a chloride. Now, reactions with water. Reaction of sodium and magnesium with water, if we are going to do it this way, I hope you understand sodium reacts vigorously with cold water. It melts into a ball of molten metal, like you can see over here. It moves across the surface of water, giving off hydrogen gas. It quickly gets smaller and smaller until it disappears. It leaves a strongly alkaline solution, pH 14 of sodium hydroxide behind. Now, since sodium is has a lower density than water, so that's why it moves across the surface of water. And this doesn't just happen to sodium. Actually, all alkali metals below it have lighter densities than water. And if we're going to talk about their densities can be quoted as 0.5 something, where water is 1 gram per cubic centimeter. So if we're talking about 0.5 gram, per cubic centimeter definitely is much lower than water. So they are supposed to float on water. So that's why whenever they are converted into molten balls like this, giving off hydrogen gas, catching flames, they actually still keep floating on the surface of water, become smaller and smaller. If you want to actually constrain them to one point, you can do that by putting up a filter paper on the top of water surface, a little bit of water on top of it, and then you can constrain sodium into one place. But that is it. Then it's going to catch fire in a really vigorous way. If you don't constrain it to a specific point, it keeps on moving the water in random directions, keeps up burning itself up and leaving behind a strongly alkaline solution. Now, using the terms like as vigorous or violent is a good way to show it, but I would ask my students that do not go for any stronger adjective than that, because you need to keep bigger and stronger adjectives for the alkali metals below it, such as they may talk about in the same trend about potassium or rubidium or cesium, and the words like explosive reaction should be kept limited to rubidium and cesium, so that you can use appropriate adjectives with appropriate alkali metals. Keep that in mind. For a trend question after an exams, it really depends upon the kind of adjective you are going to use for different elements. So using some words like you may use steady with lithium, violent with sodium, vigorous with potassium, and then explosive with rubidium or cesium, so that you can explain with the help of your adjectives about these elements, the trend going down the group and them becoming more reactive and reacting more vigorously with water. Okay. You might have already seen books doing the same. Okay, point number two. By contrast, fresh magnesium reacts extremely slowly with cold water, taking several days to produce a test tube of hydrogen gas. The solution formed is very weakly alkaline, pH 11. Any magnesium hydroxide formed is very slightly soluble, therefore, a lower concentration of OH negative aqueous ions enter the solution compared with the result when sodium is added to water, because Na2O or NaOH is highly soluble in water. So this really is a slow reaction, but when heated, magnesium reacts vigorously with water in the form of steam to make magnesium oxide and hydrogen gas. So really, I change the, if I change this, only then I can put it that way. Okay. So remember, if it's liquid, you're supposed to write this reaction. If it's gas, you're supposed to write this reaction. And since the products are different, hydroxide and oxide, I hope that makes sense. Okay, so this completes 10.3. Let's talk about their oxides a little bit more. Oxides of period 3 elements and their oxidation numbers. If I talk about in terms of oxidation numbers, it's pretty easy to understand that the metals tend to have just one oxidation number. However, nonmetals have the capability to give more oxidation numbers. They haven't exactly shown +3 with phosphorus, but it would have been right. And there are some past papers which also show +3 for it. Like it can form P4O10, it can also form P4O6. Or if I don't talk about the dimers, it is P2O5, or empirical formulas are P2O3. So this clearly tells us this one's 3, this one's 5. So yeah, this is possible. However, the book tends to not to go with this. That's fine. Even the past papers do not do it so much. They tend to stick to easier questions in this way, but specifically for inorganic chemistry. So the trend can be seen over here, and I hope you understand about the states. Now, Cl2O7, as I've said previously, is possible. So yeah, chlorine is capable of showing more states, which means Cl2O6 or Cl2O4 are also possible. Cl2O5 can be possible. Cl2O is possible. So there have been many oxides really if we talk about chlorine, and some of them are even mentioned over here. Okay, the maximum oxidation number of each element rises as we go across the period. It happens because period 3 elements in each oxide can use all the electrons in their outermost shell in bonding to oxygen, for which the usual oxidation number is -2. However, this number may change Okay, they all exist in positive oxidation states because oxygen has higher electronegativity than any of the period 3 elements. You can see section 12.2 more for more about electronegativity. Okay. However, we have done electronegativity previously, so I hope you remember that if we talk about the nonmetals, fluorine has the highest electronegativity. That was back in the bonding chapter. I believe that was chapter number 4. Fluorine has the highest negativity on the Pauling scale, being 4. Then comes oxygen, then comes nitrogen. To be exact about the table given in your book, oxygen would have been 3.5, nitrogen would have been 3, almost equivalent to fluorine, which also happens to be closer to 3. So 10.5, effect of water on oxides and hydroxides of period 3 elements. So I have discussed this point previously, but let's go move ahead. Let's discuss it in a little more detail too. So oxides of sodium and magnesium react with water to form hydroxide. Some of them form strongly alkaline solution, higher pH, weakly alkaline solution because it is very less soluble, lower pH, maybe 10, a maximum of 11. So I hope you understand why they have written it. So I've already discussed it previously, so let's move on. Magnesium oxide and hydroxide are commonly used as in indigestion remedies. For example, you can see the bottle of milk of magnesia. Milk of magnesia is a common name that we use for these products, milk of magnesia, which is usually sodium oxide or a solution or suspension of sodium hydroxide for this purpose. So whenever your stomach gives out excess acid, in order to relieve the pain, it's better to go with this or with this because these can react with the acid right then and there, and it's more like an instant remedy. It gives out a salt which is actually easily taken up by the body and water, so that actually neutralizes the acid in a very good way. Moving on, aluminum oxide does not react or dissolve in water, which is because of an oxide layer which can protect aluminum metal from corrosion. I hope we have already discussed that before back in IGCSE, how we say that aluminum is a corrosion resistant element. However, it does react and dissolve when and added to an acidic or alkaline solutions. So I hope you understand about these facts. Since it's amphoteric in nature, and actually these reactions tend to prove its amphoteric nature. Amphoteric means it can react with an alkali like an acid, or it may react with an acid like an alkali. And in both cases, it's capable of neutralizing them into salt and water, or sometimes the salts which are water soluble. So yeah, that is possible. So it may act like an acid, an alkali with an acid, or an acid with an alkali, giving us salt and water. Maybe just salt for those reactions, but proves the same point. Okay. When aluminum oxide reacts with an acid, it behaves like a base. It forms salt, aluminum sulfate. For example, in the case of sulfuric acid, if it was nitric acid, it would have been aluminum nitrate, or if it was hydrochloric acid, it would have been aluminum chloride. And they will all give out water in the same way. When it reacts with alkali, it behaves like an acid. It reacts to form a salt, which we call sodium tetrahydroxyaluminate, or simply speaking, sodium aluminate. Um, in the example given above, actually we need hot concentrated alkali in a little bit of more amount. Okay, so the compounds that act as both bases and acids are known as amphoteric. Let me tell you the examples for amphoteric uh, systems for normal elements is considered for both oxides and hydroxides. And the oxide and hydroxides commonly discussed in IGCSE are zinc oxides and hydroxides, or aluminum oxides and hydroxides, or beryllium oxides and hydroxides. However, there are one or two more transition elements for which we have some questions in past papers here and there, but those questions are pretty rare. Usually they tend to go with these examples for amphoteric oxides or hydroxides. Okay, so moving on. Silicon dioxide is also insoluble in water. Now, um, actually, before I move ahead, let me clarify. I have mentioned these so that if you need to write in a reaction of zinc oxide with an acid like this or an alkali like this, you should know how to do that. Or zinc hydroxide for that matter, or aluminum hydroxide, or beryllium oxide or hydroxide for that matter. So that's why these examples have been considered, because only aluminum oxide has been done over here. We have here six oxides and hydroxides which are going to act amphoteric in the same way. So you should be capable of writing or coming up with the equations in the same way, right? So when aluminum oxide reacts with an acid, actually I'm done with that part. So silicon dioxide is also insoluble in water. We have studied that part back with silica or sand structure back in IGCSE, as well as in previous bonding chapters of AS. So water cannot break down its giant molecular structure. However, it will react with and dissolve in hot concentrated alkali, which will result in the formation of a salt and water. So we say it reacts like an acid when it reacts with an alkali, forms a salt, in this case sodium silicate, plus it forms water. It does not react with acid, so it is classed as an acidic oxide. That's what I was trying to say earlier. So phosphorus 5 oxide reacts vigorously and dissolves in water to form a solution of an acidic oxide, phosphoric oxide, an acid, phosphoric acid. So the oxides of sulfur, they also form acids, sulfurous acid, also known as sulfuric 4 or sulfuric acid, sulfuric 6 acid to be exact with systematic names. The effect of bonding and electronegativity on the structure or acidic basic nature of period 3 oxides can be considered over here. Now, it is going to give you a very good idea of what's happening and why it's happening in the same way. So if we look at period 3 oxides, for example, sodium, magnesium, aluminum, silicon, phosphorus, or sulfur oxides, so you can see basic, this one is amphoteric really in the center, and then we have acidic ones. So if we talk about them, the melting point for ones that have ionic bonding, they have high melting point. The one that exists in a giant covalent or giant macromolecular structure are very high. You must be thinking why aluminum oxide is very high, since we have already considered this point, and because of Al plus 3 plus and strong attractive forces, these ionic bonds are supposed to be stronger than what is there in magnesium oxide or in sodium oxide. So I hope you get the previous point or the piece of detail that we have discussed previously. However, for P4 or SO2, P4O10, SO2, SO3, they're low because they're simple molecular structures. Now, the electrical conductivity is only good for the ionic compounds. Really, if it's a giant covalent compound or if it's a simple molecular covalent compound, they are not going to conduct electricity. Chemical bonding is something that I've already considered, and the structure too, so I hope that makes sense. Now, if you look at these structures, that's how giant ionic structure or the lattice is supposed to be. Alternate arrangement of positive and negative ions in fixed positions with very strong bonds, having strong electrostatic force of attraction in them. This is the structure of a giant covalent molecule. So the giant covalent molecule is extended throughout in all three dimensions, giving you a big, huge structure. So that kind of structure is very difficult to fake and resolve. So of course that would be insoluble in water. And moving on, simple molecular structures have low melting and boiling points because they are simple and smaller molecules. So I hope you understand about the van der Waals forces in them. And because of having peak intermolecular forces, they're very easy if we talk about melting and boiling. So moving on, remember that electronegativity is the power of an atom to attract the electrons in a covalent bond. A bond that has already been formed towards itself, electronegativity increases across a period. That's why the nonmetals on the extreme right, such as halogens, are the most electronegative elements on the planet and decreases down in a group. That's why among for halogens, fluorine is the most reactive one or most electronegative one in this case. So going across the period, it gives you an idea that the elements you get as more electronegative as electrons are strongly attracted by the increasing positive nuclear charge, which is pretty much explainable at this point. Since we are done with this part, I hope this makes sense to you already. Now, the electronegativity values, which indicate the strength of attraction for an atom for the electrons in a bond, and this can be shown by these values over here. And I hope you understand as we move forward in period from left to right, it increases. Okay. Now, as we go across period three, the structure of oxide changes from ionic metal oxides, which are basic oxides, to giant covalent oxides, to simple molecular oxides, which are acidic oxides. So the electronegativity of oxygen is 3.5. The greater the difference in electronegativity between period three element and oxygen, the more likely that the oxide will have ionic bonding. And that's a very good explanation of the electronegativity difference-based deductions that we made back in the bonding chapter, and we are making the same deductions over here. So, yeah, if the difference is too big, we can easily assume for a metal and a non-metal to have an ionic bond in them. Electrons will be transferred from sodium, magnesium, and aluminum atoms. They will form cations, positively charged anions, to oxygen, which is going to form an anion, O negative to 1. That's how their oxides are formed. That's how lattices, ionic lattices. However, the other period three elements will form covalently bonded oxides, in which bonding electrons are shared. Notice that the high melting point of giant ionic and giant covalent structure, leading to the use of magnesium oxide in the lining inside of furnaces. I hope you remember this specific point from industrial chemistry chapters, specifically for blast furnace. Now, we have discussed previously in IGCSE that the blast furnace inner lining is made up of magnesium oxide. That's because of its giant melting point incapable of withstanding a higher value of temperature. So aluminum oxide and silicon dioxide are used to make ceramics, the ceramics that we commonly use in the form of wash basins and other ceramics in toilets or maybe the washrooms. The giant covalent structure is designed to withstand high temperatures and provide electrical insulation. So that's the purpose we use it for. Actually, some ceramic parts for which pylons are made are also used in the high power or high voltage cables for overhead cables. We have also studied it back in IGCSE. So these kind of information, they're just noting it down because they have been previously considered in IGCSE. Moving on. The oxides of metals, sodium and magnesium with purely ionic bonding produce alkaline solutions. Why? Because water is going to accept their oxide ions in this way, forming hydroxide ions. This is the exact reason of why we say that they form uh, basic oxides. That's what happens to a basic oxide when it is dissolved in water. The oxide ion is accepted by water and they are converted into hydroxide ion upon proper reaction. In contrast, the covalently bonded nonmetal oxides of phosphorus and sulfur dissolve and they react with water to form acidic solutions. How? They tend to give away their hydrogen ions. Hydrogen ions are added to water in the form of dative bonding. This donation actually represents the dative bond that they form. So remember, the dative bond was coordinate covalent bond, and hydrogen ions were able to accept a complete lone pair of electrons from oxygen, hence H3O positive structure. HSO4, however, is going to be negative. There is a negative sign missing in this book. Okay. So the insoluble oxides of aluminum and silicon show that their acidic nature by reacting and dissolving in an alkaline solution, such as hot concentrated sodium hydroxide solution, forming a soluble salt, sometimes water along with it. So we have discussed those parts. That's why we specifically mentioned the silicon oxide as an acidic oxide. Okay. This behavior is typically of a covalently bonded oxide. However, aluminum oxide also reacts and dissolves in acidic solutions, forming a soluble salt, behavior of a typical metal oxide. Because aluminum oxide behaves in two ways, this provides evidence that chemical bonding in aluminum oxide is not purely ionic or not purely covalent, hence empathetic. Now, they mention it as a basic oxide, but don't forget, it also acted as an amphoteric oxide a couple of pages earlier. So we know that it is amphoteric. Why? Because it can act more like an acid with an alkali or more like an alkali with an acid. So yeah, both reactions were possible. And these reactions tell you that it's not purely ionic, it's not purely covalent. One of these facts have been discussed in the bonding chapter previously. We have discussed that we can't just keep everything in white and black. There is a lot of gray area when it comes to ionic and covalent bonding. And we have discussed the fact that a pure covalent bond may exist, but forming pure ionic bonds, 100% pure ionic bonds, that might not be possible. Now, we have already discussed the ionic character in covalent bonds, but the covalent character in ionic bond is yet to be discussed, and I specifically mentioned that we are going to do that in A2. So half of this has already been cleared up in AS. The rest of the half, we are going to clear that in A2. That's where A levels draw boundary lines, and we are going to keep those boundary lines intact. Moving up, we have chlorides of period 3 elements. So oxidation number of period 3 chlorides. If we are going to discuss about chlorides, it's simple and easier to talk about the oxidation number. Chlorine is going to keep its oxidation number at -1. That's how the oxidation numbers to be discussed for these chlorides for period 3 elements is pretty easy, since most of them are going to show a single oxidation state. That's not entirely true if we talk about the elements on the right-hand side, specifically for phosphorus and for sulfur. That's why he told you for that for PCl3 is also possible. Oxidation number is +3. S2Cl2, where oxidation number is +1, is also possible. So +1, +2 for sulfur, and +3, +5 for phosphorus. So yeah, sulfur and phosphorus being pure non-metals tend to do the same thing, whether it's oxide or whether it's chloride. Effect of water on chlorides of pH3 elements. This is something that we do specifically in AS. And since it's so specific, please keep in mind there are going to be questions about it. So this is considered for all three papers, 1, 2, and 3. So keep this stuff in mind for all three papers. Okay, so the formulas are right there. The chemical bonding is also there. The structures are there. I think it's pretty easy to understand since there are no giant covalent structures. So it's either divided into giant ionic or simple molecular. Now, the giant ionic are the ones which are white solids and they dissolve in water to form colorless solutions, and they tend to stick to closer to neutral or at neutral value. However, if you talk about the ones that have simple molecular structure that are based on covalent bonding, they don't actually dissolve in water. They react with water. And when they react with water, they give off white fumes of hydrogen chloride gas. Now, this is going to happen in an appropriate trend, something that we at least can discuss for these as a trend. So you can see if they're giving off white fumes of hydrogen chloride, definitely the pH is going to be lower, hence 3 or 2 pH is commonly seen for these. Let's talk about them in more detail. At the start of period 3, the ionic chlorides NaCl and GCl2 do not react with water. The polar water molecules are attracted to the ions. They can dissolve the chlorides. They break down the entire giant ionic structure. The solution formed contains the positive metal ions and the negative chloride ions surrounded by water molecules. And the metal and the chloride ions are now known as hydrated ions. This is as far as we go at this level. Since we're keeping most of this related information for A2, so it's merely a paragraph-based explanation for this one, and that's as far as we're going to go for. Since the boundary lines are pretty clear at this point, so it's easier for you to understand that we are simply going to break it down into positive and negative ions. Water is going to surround them. This part is something that we commonly known as dissolving. So now you know when you take a glass or a beaker full of water and you throw in a spoon of full of salt, which first settles down at the bottom, then you stir it up. As soon as you stir it up, what happens is that water comes closer to this. Water breaks this NaCl into Na positive ions and Cl negative ions. Something that we've already explained is that water is going to surround them from all the sides, and that the same thing is going to happen for this one as well. Since it's broken down into ions, this all tends to disappear as soon as we keep stirring. Now, something that I'd like to mention in specific, they are mentioning that the water molecules are polar, which means water is going to have slight or partial charges on top of it, which makes much more sense if I'm going to put it that way. Partial negative or oxygen is attracted to positively charged sodium, okay, but the hydrogen stays away. So oxygen is going to surround it properly like this. And all of the partially negatively charged oxygen are attracted to the sodium. That's why water is capable of breaking it down, because it can then show more attractive forces, which are more stable. We call them simply hydrated ions. So in this case, in the case of fluoride, it's going to be hydrogen every time. That's how it is going to show the dissolution process, or what we simply call dissolving process. And every hydrogen ion is actually partially positively charged over here. Hence, that gives us the idea how the polar water molecules are capable of dissolving ionic substances. The water is formed as a covalent compound as a result of covalent bonding, but the polarity in water, the slight charges present in water, partial charges, not complete charges, makes water polar and makes water capable of dissolving any compound. And hence, water is so unique when it comes to all of the solvents, and is sometimes also considered as a universal solvent capable of dissolving many covalent or ionic compounds. While if we talk about other solvents, they are very biased. Most of them tend to take on with a single approach. Either they try to dissolve ionic compounds or they try to dissolve covalent compounds. So water, though it's not the only solvent on the planet which is doing so, but of course, if we talk about the extent it is doing, yeah, it may be the only one. Okay, so moving on, aluminum chloride is sometimes represented as Al2Cl6, which is actually a dimer of AlCl3. And as we have seen in the chapter number 4, bonding chapter, this is the dative bonding I'm talking about. How do you know about a dative bonding from a dot and cross model? As soon as you see the dot and cross model, try to spot something. Try to go with the shared pairs, dot and cross, dot and cross, dot and cross. All three of these are covalent bonds. Cross cross represents a dative bond. So dot and cross, dot and cross, dot and cross, covalent bond, cross cross, dative bond. This one and this one are dative bonds. If you're looking at a structural diagram, it's pretty easy. An arrow represents a dative bond. The straight line represents covalent bond. Now, arrow is always given in such a way that the tail is pointed towards the donor of the electron pair, and the head is pointed towards the acceptor of the electron pair. So aluminum here is the acceptor. Okay. So you might be thinking aluminum is a weak metal. This should have been formed by aluminum making +3 ions and chloride making negative ions. So yeah, the bonding is shown in this way, and you might be astonished about the covalent bonding. We keep calling this one as a weak metal, so or a light metal. So why are we doing it this way? This gives you a pretty good idea why we are doing it this way. Plus, this is something for which the heads up was given in the previous portion, that it is the kind of substance that for which we have the amphoteric part, not purely ionic, not purely covalent. So yeah, we show it with covalent bonding, but that won't be a complete representation either. For amphoteric, this is difficult to represent with a single way. So we'll tend to keep on with this kind of bonding, since that's a part of your book. Okay, as we go across period three, the structure of chlorides change from ionic metal chlorides, which are neutral, to metallic chlorides, which can be hydrolyzed by water to form acids as one of the products, to simple molecular chlorides, which form acids when added to water. Okay. So the ionic metal chlorides, sodium and magnesium, metallic chlorides hydrolyzed by water, aluminum, simple molecular chlorides, phosphorus or silicon or sulfur, all of them. Okay, so I hope this is pretty clear. However, let's clarify this. I guess I skipped a point, so let's clarify. Aluminum chloride is represented as AlCl3. This suggests that this chemical bonding is likely to be Al positive free and Cl negative ions in giant lattice. In solid hydrated aluminum chloride crystals, this is the case. However, without water, it exists as Al2Cl6. This can be thought of a dimer, two molecules joining together of AlCl3. This then becomes a covalently bonded molecule. So here they are differentiating between both the cases with and without water. That's why the hydrolyzed portion, I think this clears it up. Once we add water, the dimers are broken down, aluminum ions and chloride ions enter the solution. Each relatively small and highly charged aluminum ion is hydrated, first though a water molecule bonded to it lose an H positive ion. This turns the solution acidic, and we can show this in the following equation. Now, these signs, these large brackets, they actually tend to show complex bonding. Complex bonding is something that we haven't studied over here yet. We're going to study it as a part of A2. So just for now, let's go on with the equation without explaining it in more detail. However, I hope you do understand out of the six water molecules it has, five take there in the same form, and one of them is broken down into H positive, which is going to turn the solution slightly acidic. Not very acidic, but yeah, slightly acidic. Okay. So non-metal chlorides, SaCl4, PCl5, they all are hydrolyzed in water. They release white fumes of hydrogen chloride gas in a rapid reaction. This is what happens. And these are the white fumes that we have been talking about. SiO2 is seen as the off-white precipitate. Some of the hydrogen chloride gas produced dissolve the water in the water, leaving an acidic solution, hydrochloric acid, which can, of course, convert the litmus paper into red. Now, this diagram can give you a pretty good idea why we were talking about the gas forms or get the gas clouds or white fumes. So you can see the white fumes. For phosphorus, the same thing happens. Both products are soluble in water. In case of phosphorus, this is a combination of actually two acids right there. Though this is shown as a gas, but you know this gas is highly soluble in water and it's going to give us an aqueous solution of hydrochloric acid. So that's actually a combination of two acids right there. That's why in case of PCl5, it's going to be highly acidic. Okay. I guess that's about it. I guess there is no information for sulfur, which gives you the idea about that. Okay, so 10.8, last topic for the chapter, deducing the position of an element in the periodic table. So we can deduce the possible position of the element by looking at its physical and chemical properties. We can also predict like Mendeleev predicted back for physical and chemical properties for a given group if we know its position. Worked example, there are several ways of arriving at the same conclusion, and we have discussed those. So element G forms a chloride, which reacts with water to form a solution of pH 1, must be acidic. It forms an oxide which has a melting point of 1610 degrees centigrade. The oxide does not dissolve in or react with sodium hydroxide solution. Deduce the possible position of G in the periodic table. Let's use the pH data to decide whether G is likely to be a metal or non-metal. Low pH suggests that it is a metal chloride which undergoes hydrolysis, so it is likely to be as a part of group 13 to 17. Okay. Using the solubility data, the oxide doesn't dissolve in sodium hydroxide. This rules out aluminum oxide because aluminum oxide does react with sodium hydroxide and forms an aqueous salt. Let me tell you that the reaction for Al2O3 back with NaOH was to give you NaAlO2, which was more soluble in water, and then there is an OH compound. So since this becomes soluble later with sodium aluminate, so this gives you the idea that this can't be aluminum oxide. Okay, using melting point data, the melting point is high, so it is likely to be a giant covalent structure. If it's not group 13, based upon the fact of melting point, it can't be 16 or 17. The 16 and 17 are simple oxides of simpler structures, so that's not possible. Let's stick to group 14. Can't be in period 2 because CO2 is a gas, so it's period 3 or lower. Make sense?
Yes, sir.
So this must be either aluminum or any element below it, possible position. Uh, Book discusses worked examples that gives you multiple lines. Usually there tends to be just one or two lines. Okay. So selenium is in group 16 and period 4 of the periodic table, predicts some of its physical and chemical properties. Identifying the likely structure of selenium from its position in the periodic table in comparison with other group 6 elements. It's a non group 16 elements. It's a non-metal since it's group 16. So comparing with sulfur, it should have a simple molecular structure. Identifying the physical properties, simple molecular structures have low melting points. They do not conduct electricity. They're not soluble in water either. Identifying the chemical properties with reaction with water or reaction with chlorine or oxygen. Simple molecules do not react with water. It reacts with chlorine. It is going to form a simple molecules, just like silicon did, sulfur did back there. But sulfur was capable of making a different kind of chloride than this one. Don't worry about that. You may come up with a formula. Sometimes they don't tend to ask the formula. Even if they do, they give students the option that either of the formula can be correct. So if you're gonna think about sulfur and if you're gonna put it like this way, okay, so it doesn't exactly mean yet that you need to come up with an exact formula. Since they're non-metals, they might be able to form more chlorides or oxides. So any of those formulas, if exist, work. So reacts with oxygen to form a possible formula, and he is specifically mentioning this phrase so that you can compare it with sulfur and you can form it in the same way. Since SO2 exists, so possibly SeO2 also exists. Okay, this gives you the idea how to identify physical and chemical properties. I hope I have made the point clear, right?